So I'd like to thank the organizers for giving me the opportunity to give lectures at this nice workshop on unifications of integral systems. So my talk title is the Courant-Hilbert construction in 4D Chern-Simons theories. So probably, so as you know, the name Courant and Hilbertos. So this is the authors of a nice, famous textbook, Methods of Mathematical Physics. And so the one method listed in the textbook is related to my talk. So that's why Courant Hilberto is included in my talk title. So I have two talks today and tomorrow. So the first talk today, so I would like to introduce what is the Courant-Hilbert constructions. So first of all, so I would like to introduce the basics on the TT bar deformation. Deformation and root TT bar deformation. Theoretical physicists are familiar to these subjects, but I think that some of you are not so familiar to these subjects, and so I'd like to start with the basics of these deformations. So I would like to explain the Courant-Hilbert constructions of integral deformations of two-dimensional principal chiral model. 2D principal chiral model. Okay. So this Courant-Hilbert approach contains TT bar deformations and root TT bar deformations. So this Courant-Hilbert constructions in two-dimensional principal chiral model was invented by Babae and Bin Chen and Son Heisans by Nimbo group. Babae. Et al. This is a very recent paper. So today's content is basically based on this paper. So actually, so the contents of this Courant-Hilbert constructions in three-dimensional principal chiral model is closely related to the auxiliary field sigma model. So this is abbreviated as AFSM. This was invented by Felk and Smith last year. This auxiliary sigma model was proposed as integrably deformed principal chiral model. So this FSM describes very general deformations of principal chiral models by including auxiliary fields and arbitrary functions. So auxiliary fields are included. So that's why the name is auxiliary field sigma model. And so by taking a variations with auxiliary fields, we will get some constraints. But so some constraints are automatically satisfied by following this Courant-Hilbert approach. So this is a very important point. So unsatisfactory point of this FSM is that it is very difficult to integrate out auxiliary field completely. So, but without using auxiliary field, we can do the same things by following the Courant-Hilbert approach. So this is a very strong point. So anyway, so I would like to explain about this Courant-Hilbert approach in this talk. And tomorrow, I would like to explain Courant-Hilbert Courant-Hilbert approach in four-dimensional Chern-Simons theories. So this is based on the collaborations with Osamu Fukushima at Riken Items and Takaki Matsumoto at the Seikei universities. This is our recent paper, recent work, this one. So this Matsumoto is Takaki Matsumoto, and so not Takuya Matsumoto sitting there. And so, yeah, this is another Matsumoto. And okay, so anyway, so tomorrow I would like to explain about derivations of two-dimensional principal chiral models from four-dimensional Chern-Simons theories. And so then, so I would like to introduce generalized Lux ansatz. By following the knowledge on Courant-Hilbert constructions in two-dimensional principal chiral model. So then, according to these generalizations of Lux ansatz, we can discuss the Courant-Hilbert constructions in the context of four-dimensional Chern-Simons theories. And so then, so as a result, we need a correction term depending on the deformations. I mean, depending on the choice of the deformations. So this correction term is nothing but the trace of the energy momentum tensor. So this correction term was also found by Sakamoto and G. Sakamoto sitting there, and Robert Tateos and Masahiro Yamazaki in this paper. For TT bar deformations. So this result is consistent to our Courant-Hilbert construction results. So anyway, so this is the contents of tomorrow lectures. And so today, I'd like to explain about the Courant-Hilbert constructions of integrable deformations of three-dimensional principal color models, basically by following this paper by Babae et al. Okay, so then, first of all, so let me introduce the basics on TT bar deformations and root TT bar deformations. So actually, so the developments of these deformations are closely related to the discovery of this Courant-Hilbert approach. Okay, so first of all, let's assume the set of two-dimensional quantum field theories described by Lagrangians. Assume 2D quantum field theories described by Lagrangian. So here we assume the existence of the Lagrangian description. So then consider trajectory in the theory space parameterized by parameter alpha. This space. So we denote the Lagrangians at each point L alpha. Okay, so then we will consider a flow for this L alpha. So here I would like to introduce the TT bar operators. Define. This is a determinant of energy momentum tensor, like this. So then GG component, G bar component of energy momentum tensors, and the square of trace. So originally, this TT bar operator was proposed by Sasha Zamolchikov irrelevant perturbations for conformal field theories. So then, the trace part vanishes. So then, this GG component of T is usually described as T. And so G bar component of energy momentum tensor denoted by T bar. So that's why this operator was called TT bar operator. So nowadays, this TT bar operator is considered for deformations of non-conformal field theories. So the trace part does not vanish always. But conventionally, this operator is called TT bar operator. Okay, by using these TT bar operators, we can consider a flow for this Lagrangian. So that is nothing but a TT bar flow. The TT bar flow is defined by these ones. Del alpha plus del alpha equals del alpha to point del alpha determinant T mu alpha. So, okay, so this is the definitions of TT bar flow. So this is rewritten like this. Del alpha TT bar alpha. So the alpha attached to this TT bar operator, so energy momentum tensor, means that this energy momentum tensor is for the deformed theories, L alpha. So this TT bar flow, the definitions of TT bar flow is given by this one. So this one may be a bit weird because deformed theory is shifted to infinitesimally deformed L alpha plus del alpha. So deformed theory is slightly deformed theory. So the picture of this flow is like this. So this is UV and this is IR. So this point, alpha corresponds. So then, this L alpha is slightly shifted. L alpha plus del alpha, like this. So then, the alpha 0 corresponds to this endpoint. So this L0 corresponds to G undeformed theory. So, okay, so this is the interpretations of TT bar flow. And actually, there are two kinds of interpretations of TT bar flow. So these interpretations of TT bar flow is called new interpretations. So the old interpretation is like this. So alpha equals 0 is inserted. Then alpha TT bar 0. So this TT bar operator is composed of the energy momentum tensors for the undeformed theory. So the alpha equals 0 is put to this ones. So the original old interpretations of TT bar flow, the deformation started from here. But nowadays, according to new interpretations of TT bar flow, the definition is start from the intermediate point, L alpha. So the original proposal by such as Molchkov, so this L0 was CFT. So this TT bar operator was proposed as irrelevant deformations of conformal field theories. This is original proposal. But nowadays, interpretation is slightly different. So please note that this point. So then, I would like to introduce TT bar flow equations. Okay, let's go to the next. The definitions of the TT bar flow is rewritten into flow equations. TT bar flow equation. So this is defined by these ones. Minus TT bar beta alpha. So this flow equations was found by Smirnov and Zamolchkov. In 2016. And independently by Roberto Tateo's Torino's group. About the Okay, so these are the references for TT bar flow equations. So actually, so these TT bar flow equations was directly derived by starting from certain expressions of CDD factors. In integrable QFT. So as you know well, so in integrable quantum field theories in two dimensions, so the arbitrary S matrix is decomposed into the product of two-body S matrices. The two-body S matrices can be determined by using by following the way of S matrix bootstrap. So by imposing Lorentz symmetries and unitarities or symmetries, Cauchy symmetries or Yang-Baxter equations. And so then we can determine almost expressions of the S matrix, two-body S matrix. But there should be the CDD factor ambiguities. So this CDD factor ambiguity is very important to define the exact S matrix. So actually, so the CDD factors, by changing the CDD factors, so we can discuss the deformations, irrelevant deformations. So this is the original ideas by these peoples. So then, so by starting from certain CDD factors, so they succeeded in deriving this TT bar flow equations. Okay, so then So I want to fix the terminologies. So the deformations with TT bar operator is called TT bar deformation. Okay, so I would like to list up some properties of TT bar deformations. So first of all, TT bar operator is well defined only in two dimensions at quantum level. But of course, you may consider TT-bar operators in arbitrary dimensions at classical level. So there is no obstacles to consider TT-bar operators in arbitrary dimensions at classical level. But at quantum level, only three-dimensional space is possible to consider a well-defined TT-bar operator. And especially the quantum integrability is preserved under this TT-bar deformation. Quantum integrability is preserved by definition. It is simply because the modifications of CDD factors does not change the factorizations of S matrix. And so that's why quantum integrability is obviously preserved. Okay, then okay, so at this point, I said already, but I want to write obvious explicitly. So this TT bar deformation is well defined. At classical level in arbitrary dimensions. So of course, classical integrability is preserved as well. So then, so at some point, so TT bar deformations has been considered for general two-dimensional quantum field theories. So this is a leap of logic. So anyway, so the original proposal was only for integral QFTs in two dimensions. But nowadays, TT bar deformation is well studied for general two-dimensional quantum field theories beyond the integrability. So this is a leap of logic. So this means that so we need to be careful for the definitions of dispute theories at quantum level. So by performing TT body formations, so we will get a lot of higher derivative, and so the time derivative, a lot of time derivatives are included for the deformed Lagrangians. So then, so we are not so sure for the well-definedness of the Hamiltonians. So especially, so we are not so sure what is the correct Hamiltonian at quantum level. So of course, so the in the context of two-dimensional quantum integral field theories, so the energy eigenvalues can be computed by using beta ansatz. And so the theory itself can be defined by beta ansatz itself. And so we are not so sure for the general case, but at least for this integral case, we can really define the system at quantum level. But now, so if we consider the TT-body formations for general quantum field theories beyond integrabilities, so we need to consider the energy eigenvalues beyond without using the beta ansatz. And so we are not so sure for the well-definedness of deformed theories at quantum level. Of course, we concentrate on the analysis at classical level. There should be no problem. But we should be careful if you want to consider the quantum descriptions of the deformed theory. Okay, so uh-huh. So I have no time, so I will not explain about the examples of TT-bar deformations. So, uh-huh. So the famous examples of TT-bar deformation is Namu-Goto actions. So if we start from free theories, free massless scalar field theories, after performing the TT-bar deformations, we will get the Namu-Goto actions. So here, so I forget about the I forget I forget to explain about the dimensions of this deformation parameter alpha. So the dimensions of this alpha is the length square. So that's why so this perturbation is irrelevant. And so this parameter alpha is nothing but alpha prime in string interpretations. This is just a string slope alpha prime. So the dimension is also length square. And so this is landmark examples of TT-bar deformations. So by performing TT-bar deformations for this free massless scalar field, we will get the Nabu-Goto actions with static gauge. Sorry. So without any gauge fixing, Nabu-Goto action has a vanishing energy momentum tensors, and so TT-bar deformation is not defined. But the resulting action is Nabu-Goto actions with static gauge. So I will skip the derivations of these Namu-Goto actions. But anyway, so this is the landmark examples of TT-bar deformations. So actually, so according to these examples, so the TT-bar deformations got popular. So a lot of people studied about TT-bar deformation. Okay, so let's finish the introductions of TT-bar operators So let me introduce the root TT bar operators. So root TT bar operator is very close to TT bar operators, but uh, of course are different. So the name of root TT bar operators is uh, very nice probably. So as it is actually root TT bar information. So the root TT bar operator is defined by this one. So this is a determinant of t tildes, and so we need to take square root like this. So here, t tilde mu nu is the energy momentum, traceless energy momentum tensor. Defined by like this. So by taking the determinant of this traceless energy momentum tensor, and by taking square root of this, and so then root TT bar operator is defined like this. So actually, so this root TT bar operator was proposed by a lot of researchers almost simultaneously. So here, I would like I would like to follow the notations by Felco et al. Means 10515. Okay, these papers. And so this operator was proposed by other peoples almost simultaneously. But here, I will write one of them. And basically, so I will follow the notations of this paper. So then, so we can consider the flow equations by using this root TT bar operator. So this is called root TT bar flow. So this is something like this. So please note here that so this flow equations was not derived from CDD factor. So this is just a natural generalization of TT bar flow equation. Now this is a natural definition. Okay, so that's why, so this root TT bar flow equations is not directly related to the CDD factors or quantum perspective. So this classical, this root TT bar flow equations is well defined at classical level, of course, but we are not so sure for the quantum descriptions of these root TT bar deformations. So this is very infamous issues in this root TT bar flow equation. So I want to list up some properties of root TT bar deformations. Oh, hmm. So remarkably, so we took the square root of these determinant operators. And so now, so the deformation parameter gamma is dimensionless. So this root T bar deformation is marginal deformations. At classical level. Of course, at quantum level, this marginality is broken. And so this is just a statement at classical level. So then, the second properties, the classical integrability is preserved under the root T bar deformations. Classical integrability is preserved. I think that so this statement is not so trivial, but this classical integrability was proven by Bolzat-Felco and Spondolini, this paper. Four, 274. Okay. So these papers. So then, so as I said already, quantum integrability is unknown. And uh, indeed, not marginal. Okay, so then, so I want to note about the relations between root T bar deformations and four-dimensional nonlinear electrodynamics. So four-dimensional nonlinear electric dynamics is beyond this talk, but so this root T bar deformation has been well studied in the context of four-dimensional nonlinear electrodynamics. In four-dimensional nonlinear electrodynamics. So this is abbreviated as NLED, like this. So this, okay, so we can consider the root T bar deformations of four-dimensional Maxwell theories. So we can consider the root T bar deformations. So at classical level, we can consider arbitrary dimensions. And so we can consider root T bar deformations of this four-dimensional Maxwell theory. So then, four-dimensional mod max theory is obtained. So this mod max theory is was found by Townsend et al. Almost 5 years ago. Inbounds. Uh, so Townsend, 2007, 09092. So in these papers, so almost 5 years ago. So this is very interesting, remarkable examples of root-TT bar deformations. So I'd like to write down the classical actions of these four-dimensional mode max theories. So this is given by this one. So this gamma is a dimensionless constant, and so this inch gamma root s square plus e square. And S is defined by the usual Maxwell Lagrangian. P is defined by FF tilde, F mu nu, F tilde mu nu. This F tilde mu nu is defined by the usual Hodge dual. Okay, so when gamma equals 0, so this becomes 1 and this becomes 0. So the only S remains. So this S is nothing but the Maxwell Lagrangians. And so the gamma equals 0 corresponds to four-dimensional Maxwell theory. So this is very famous examples of root-TT bar deformations. This is a very nice applications of root-TT bar deformations in the context of four-dimensional nonlinear electrodynamics. So after that, so the Townsend et al. Considered the more general deformations of these mode max theories by combining TT bar deformations and so two-parameter mixed deformations. And so then after that, so they got ideas to apply the Courant-Hilbert method in this context, in the context of nonlinear electrodynamics. So after that, Babaye et al. Noticed that the Courant-Hilbert constructions can be applied to the two-dimensional principal chiral model. So this is historical reasoning. And so anyway, so this development was very important for the integral systems. So okay, so for remaining time, so I'd like to explain about the integral deformations of two-dimensional principal chiral model. Modmax theories.
Yeah, Modmax theory. What was the motivation? Well, of course, spheroid is somewhat similar to Born-Infeld.
Yeah.
But not precisely, right? So
actually, so probably so from long time ago, so some people addicted to finding out more general deformations of Maxwell theories. So, for example, the most general self-duals and conformal actions. So, according to the statement, this four-dimensional Modmax theory is the most general actions, preserving the self-dualities and conformal symmetry.
I see. For example, naively, if you take an nth power and then take an nth root, it doesn't satisfy that criteria. Like
I mean, so this
yeah, S cube, for example, plus P cube, sorry, P not gamma P, I guess, yeah, and then take a third root, for example. It doesn't satisfy that criteria.
No. So this is conformal, right? So the gamma is dimensionless, and so the self-duality invariance is not obvious, but so this action satisfies the self-duality.
I see. But just a statement that if you impose self-duality and conformal invariance, this is the only
according to the
deformation of the Maxwell theory.
Yeah. according to their paper. So this should be the
I see.
most general, yeah.
Okay, thank you.
So anyway, so according to the developments in the study of four-dimensional non-reactive dynamics, so we got a nice progress in studies of integral deformations as well. Courant-Hilbert in the principal chiral model. Y8 well, 07.22808. So actually, so the explanations of this part is very brief, and so it will not take time so much. And so the deformed Lagrangian is given by this ones. L hat curly f is the functions of x1 and x2. And here, I need to define x1. This is a trace j mu, and x2 is defined by trace j mu, trace j mu. Here, j mu is the usual left invariant one form, Maurer pattern one form, and this G is a group element G. So now we are considering the G principal chiral models. So here I have introduced two quantities, x1 and x2. These are Lorentz scalars. And so these two Lorentz scalars are functionally independent. So actually, so these variables were utilized by Felcott et al. To compute the root TT bar deformed actions. So by using these variables, so they succeeded in deriving the explicit form of the root TT bar deformed actions. So this is the paper 0515. Okay, so anyway, so it is very useful to use these variables. So then deformed Lagrangian is written the functions of x1 and x2 like this. And so then Lux pair. Oh, okay, so there is no space, but Lux pair is defined by like this. D and curly j plus minus 1 minus g squared. Of course, g is a spectral parameter. So please note that pole structures of the Lux pair is slightly different from the usual principal chiral model. So the spectral parameter appear here, and so this curly j is arbitrary functions. So this curly j is equal to small j. So then this 1 plus minus g is reduced. And so then we can derive the original form of the Lux pairs for the principal chiral model. So in that sense, so this inclusions of curly J is a kind of deformation of the principal chiral model. So anyway, so the pole structures of this Lux form is slightly different from the familiar one. So this is very important observations. So then this curly J is defined del 1 curly F J mu plus 4 del 2 F J nu, sorry, J mu, J nu. So this is the definitions of this curly J. So this curly J is written in terms of curly F. Curly F is this L hat. And so the del 1 is a derivative with x1. So this derivative is respect to x2. So we are not so sure for the mathematical rigorous formulations of this derivative, but let's consider the formal derivative x1 and x2 like this. So then J mu is given like this. So then, the flatness, I mean, classical integrabilities needs satisfies these differential equations. x1 del 2f square minus 4 2x2 minus x1 square f equal minus 1. This is very important relations. So anyway, so by finding out curly F satisfying these differential equations, we can fix this current J mu. So then Lux pair is determined. So of course, F itself is classical Lagrangian itself. So the deformed Lagrangian is also fixed. So the remaining task is just solving these differential equations. So by solving these differential equations, we can get deformed Lagrangians and associated Lux pair. So this is the scenarios based on the Courant-Hilbert constructions in principal chiral model. So here, so what is Courant-Hilbert? That is remaining of my talk. So here, let's introduce new variables. This is u in point 2x2 minus x1 square minus x1. And v is defined by this one similarly, plus x1. Okay, so then the relations, these ones, can be rewritten into this simple form. Del u f del v f equal minus 1. So this is a very simple way. This is a very simple form. So actually, so these differential equations can be solved. And so the most general solution has been found by Courant and Hilbert. So that's why this method, this scenario is called the Courant-Hilbert construction. So the general solutions is written in the famous textbook, Methods of Mathematical Physics by Courant and Hilbert. So the general solution is L prime tau F0V or so this is general solutions to these differential equations. So then, so the scenario is very simplified now. So by providing explicit form of L. So then we can fix this curly F. So actually, interestingly, these coordinate transformations was found by Gaillardo and Zumino. FTH, sorry, Q7, Q7, 12103. So 1997, so the Zumino found this nice Fourier transformations. This Courant-Hilbert problem was found by them in the context of four-dimensional nonlinear electrodynamics. But at that time, there was no root TT deformations and modmax theories. And so only solution was Bolognese action, Bolognese type deformations. So this was quite early. But this coordinate transformations was found by Townsend et al. To deform the Maxwell theories. So, but after that, Baba et al. Noticed that by using these coordinate transformations to deform two-dimensional principal chiral model. So these variables are very nice, and so we can get very non-trivial deformations of principal chiral model. Okay, so anyway, so okay, so I'm running over time. So let me explain some examples. So F tau equal tau. So this is a very simple one. So then, so F equal V minus U is nothing but the x1 half. And so this is nothing but the two-dimensional principal chiral model. So this corresponds to the undeformed case. So the second case is exponential gamma tau. So we can include some constant here. So the gamma is a dimensionless constant. So then, so F is given by exponential gamma V minus exponential minus gamma U. So this is nothing but root TT bar deformed principal chiral model. So this was already obtained by solving the root TT bar flow equations, Bolsat et al. So, okay, so then let me provide the last examples for TT bar deformations. Actually, there are a lot of examples, but here I want to provide solutions corresponding to TT bar deformations. So that's examples. Minus 1 plus 2 lambda tau. So then F is a bit complicated. X1 plus 1 lambda square, X1 square minus X2. So this is nothing but the root TT bar deformed principal chiral model. Sorry, TT bar deformed principal chiral model. This was obtained by Chern et al. By solving the TT bar flow equations. That result can be reproduced by considering the Courant-Hilbert problem like this. So anyway, these are the very famous examples, but by considering more non-trivial answers to these Courant-Hilbert solutions, we can get much more complicated integral deformations. And actually, these integral deformations is almost parallel to the auxiliary field sigma model, because by taking these current answers, the conditions for the J plus J minus, I mean, auxiliary field sigma model, these two constraints are very important to ensure the classical integrability. So this condition is automatically satisfied by taking these expressions of curly J. And this relations is nothing but these flatness conditions. So that's why the constraints are obtained by taking variations of auxiliary fields in the context of AFSM automatically satisfied by solving these differential equations. So this means that this Courant-Hilbert deformations does not change the twist functions. So the twist function is not deformed under this deformation. Okay, so I'm running over time, so I'll stop here. Thank you so much.
Thank you very much. So is there any question or comment? So can I have one quick
Yes.
question, or
Please.
how to say? So anyway, so these are the T bar deformed ones, and so as you as a so this is a root T bar deformed one.
root T bar deformation. Yeah.
So as you mentioned, so these are classically integrable.
Yes.
But the quantum integrability is not obvious.
Quantum integrability is quite unknown for root T bar deformations. So actually, the root T bar flow has not been derived by considering the CDD factors, or we are not sure for the quantum origins of the root T bar deformations. But in comparison to that, we know well the quantum origins of TT bar deformations, so we can consider the quantum level analysis for TT bar deformations. But okay, so thank you for the introductions. So in this talk, I'd like to talk about the Courant-Hilbert constructions or integral deformations of two-dimensional principal chiral model in the context of the framework of in the context of Chern-Simons theories. So this is mascot characters of Saitama universities, and so this is called Merinchen. And okay, so anyway, this talk is based on papers this month. So this is collaborations with Osamu Fukushima at Riken Items and Takaki Matsumoto at Seikei University. Okay, so then let me begin with the introductions. So I want to start from two developments in the field of integrable models. So the first one is, as you know well, the four-dimensional Chern-Simons theories. So this is a unified descriptions of two-dimensional integrable models specified by meromorphic functions. So by choosing meromorphic functions, we can reproduce various two-dimensional integral models. So this is a very interesting point of these four-dimensional Chern-Simons theories. So this four-dimensional Chern-Simons theories was proposed by Costello and Yamazaki in these papers. So then, there is a nice ways to describe Yamazaki deformations or various integral models was shown by Delta, Lacroix, Magro, and Bicedos in this paper. So then, the second one is unified descriptions of integral deformations based on the Courant-Hilbert constructions, as I explained yesterday. So this way was found by Babae et al. In these papers. So this is a nice way to describe integral deformations of two-dimensional principal chiral models. So as I explained yesterday, so this way is based on the Courant-Hilbert method. So, and this deformations includes very famous TT bar deformation or root TT bar deformations. And so this deformation is very interesting. So then, today's topic is to unify these two developments. So how can the Courant-Hilbert method be described in the context of four-dimensional Chern-Simons theories? So we answered to these questions in this paper. So the Lux ansatz should be generalized to incorporate the deformed theories. So then, as a result, the original four-dimensional Chern-Simons theory actions need to be modified by adding some terms. So this result is consistent with new papers by Sakamoto-kun sitting here, and Roberta Teos and Masahito Yamazaki, this paper. So then, this is the contents of my talk. So first of all, I would like to give a brief review of four-dimensional Chern-Simons theories. So then, I'd like to explain how to generalize the Lux ansatz to incorporate the modified theories. And so then, as a result, we will get a correction term to the original Chern-Simons action. So then, this is some repetitions of yesterday's lectures. So yesterday I had no time to explain the Courant-Hilbert constructions well. So I would like to explain the Courant-Hilbert method briefly again. So finally, I will summarize my talk. Okay, so then let me introduce the four-dimensional Chern-Simons actions. So the four-dimensional Chern-Simons theory action is given by these ones, as you know well already. So the Benoit and Masahitos explained these actions well. So I don't have to repeat the explanations of these actions. But so, okay, so anyway, so this is the classical actions of four-dimensional Chern-Simons theory. So this CSA is the usual Chern-Simons form, and this omega is a meromorphic one form. So then, this omega is a 1,0 form. So this action has an extra gauge symmetries given by this one. So then, by using this, G component of A can be removed like this. So this was already again and again. So probably so you are now familiar to this operation. So then, by taking variations of the classical action, we will get the equations of motions. So there are two kinds of equations of motion. The first one is called the bulk EOM, and the second one is called boundary EOM. So here, so the boundary means the locations of the poles on the CP1. So of course, the CP1 has no boundaries, but so this boundary EOM has support only on the poles on CP1. So in this sense, so this equations of motion is called boundary EOM. So this is the conventions in this field. So anyway, so I want to make some notes. So if bar phi is smooth, the boundary UM is trivially satisfied because the omega is evaluated like this. So then, so bar phi is smooth, this part vanishes. So then, so the omega is 0, so this boundary UM is trivial. But if bar phi has poles, so we can get the delta function contributions like this. So then, so this boundary EOM has non-trivial contribution. So as a second note, so similarly, zeros of bar phi in the bulk EOM, these ones also plays an important role. Yeah, because so these expressions allows the gauge fields to have some poles. So because if we have poles, so then so if we contains the derivative of A, so then delta function contributions may appear, but such delta functions can be killed out by this formula. So then, so by using these two simple formulae, we can enjoy some gains to reproduce some theories. starting from these equations of motion. Okay, so then let me introduce Lux form by performing the gauge transformations to gauge field A like this. So then we can introduce the Lux form L like this. So in taking these gauge transformations, we can choose some gauge conditions like this. So G bar components of L should vanish. So then the Lux form L is simplified to this form. So this Lux form has only two components, tau components and sigma components like this. So G components and G bar components are deleted by using the extra gauge transformations and this gauge transformation. So then the original four-dimensional Chern-Simons actions can be rewritten into this form. So now the action is simplified, and so you will see the Wess-Zumino term here, but still this action is defined in 4 dimensions. So then by performing the complex integral over CP1, the 4-dimensional system is reduced to 2-dimensional systems. So by following this paper. So then we will get the master formulas to describe 2-dimensional systems. So this is the master formulas obtained by Deldac, Lacroix, Macro, and Bisedo in this paper. And this P is a set of poles of meromorphic functions bar phi or omega. So this 2-dimensional action has measures only on this P. So this action is defined only on the set of poles of bar phi. Okay, so then, now we have not explained about the explicit form of the Lux form, but according to these formulas, by computing some residues here and here, we can get the resulting actions in 2-dimensional theories. So the remaining problem is to fix the explicit form of the Lux form somehow. So usually we put simple ansatz to determine the form of the Lux form, something like this. So sigma plus and sigma minus are right-hand coordinates. So tau and sigma are coordinates for 2-dimensional Minkowski spacetime M. And now we have introduced the right-hand coordinates like this. So this G is a set of zeros of meromorphic functions. So this G is separated 2 parts somehow. So it depends on our choice. So then the zeros are assigned to sigma plus and sigma minus directions, like this. So then V plus and V minus, E plus and U sigmas are smooth functions. And this pole structure is simply taken as usual. So this type of pole structures of the Lux pairs is very popular to describe the Lux form in principal chiral models or some rational class integrable models. So what I think that this is not a unique form. So of course, so this Lux ansatz should be consistent to the bulk EOM and boundary EOM. But so this is just a simple ansatz to determine the Lux pair. Okay, so anyway, the pole structures of this L is consistent to the zero curvature structures, zero structures of phi, and so the bulk consistent to the bulk EOM. So then unknown functions are determined by the boundary conditions on the gauge field. So here, so I will not explain in general, but I will explain how to determine this Lux form by taking examples to dimensional principal chiral model later. Okay, so then let me provide the recipe to derive two-dimensional integral models from four-dimensional Chern-Simons theory. So first of all, we need to prepare a meromorphic one-form. So then the pole and the structures of this meromorphic one-form are very important to determine what two-dimensional integral model is obtained. So anyway, so the choice of meromorphic one-form is crucial to what two-dimensional integral models are obtained. So then we need to impose boundary conditions of gauge field A as the poles of meromorphic functions. So then possible boundary conditions are governed by the boundary UM, and actually, so there are some choices for boundary conditions. So simple boundary conditions, we can get the principal parallel models. And so as more non-trivial examples, we can consider Yang-Baxter deformations. So the R operators should satisfy this boundary UM. And so that is nothing but the classical Yang-Baxter equations. And so this was pointed out by Benoit's work. And so anyway, so the boundary conditions are very sensitive to the boundary UM. So then we can determine the explicit form of the Lux form by using the informations 1 and 2. So then by using the master formula of this one, so then by computing some residues, so we can get the two-dimensional action. So this is the scenarios based on the four-dimensional Chern-Simons theory. So actually, so this was explained in Benoit's lectures yesterday, and this is just a repetition, but okay, so anyway, so this is a recipe to derive two-dimensional integral models from four-dimensional Chern-Simons theory. So then, so let me explain simple examples how to derive two-dimensional principal chiral models with Zumino terms from the four-dimensional Chern-Simons theory. So for this, we will take this meromorphic one form. So this capital K and small k's are real constants. So then G equal K and infinities are double poles. So the set of the poles P is given by this one. So then G equal plus minus first order zeros of this omega. So the set of zeros is given by this one. G is composed of plus 1 and minus 1. So then we will take the boundary conditions of the gauge fields as the poles K and infinities like this. So then, after performing the complex integral, the group element G hat is restricted like this as a poles. So I have not explained about the residual gauge symmetries. But by using the residual gauge symmetries, one of them can be set to 1. So at G equal infinities, the group element is set to 1, and so this is ignored. So then the group element as G equal K is described like this. So then the boundary conditions can be rewritten into this form as G equal K and G equal infinity. So these should be zeros. So these are the explicit form. So then from these second conditions, U tau and U sigma should be 0. So then the Lux form is simplified like this. Now zeros are assigned plus and minus. So there are two zeros, but one is assigned for plus and the other is assigned for minus. So this is a simple assignment to compute the Lux pair. So then, by substituting this Lux form to these first conditions, so then we obtained explicit form of v plus minus 1, like this. This small j is left invariant one form as usual. So then the Lux form has been completely determined like this. So this is nothing but principal color models Lux pair. So then, by putting this Lux form into the master formulas and by computing some residues, we will get this resulting action. So this capital K is nothing sigma model coupling, and small k corresponds to the level of Wess-Zumino term here, the coefficient of Wess-Zumino term. So this is simple examples how to derive two-dimensional principal color model with Wess-Zumino term from four-dimensional Chern-Simons theory. So in the following, we would like to consider how to generalize the Lux ansatz in order to incorporate TT-bar deformations, root TT-bar deformations, or more general Courant-Hilbert constructions. So that is the goal of my talk here. So questions so far? Okay, so then let me explain how to generalize Lux ansatz in the previous argument. And so how four-dimensional Chern-Simons actions should be collected. Okay, so then, in the following, let's consider the deformations of principal color model again. So we start from this meromorphic function again. So, but for simplicity, capital K is set to 1 and the small k is set to 0. So we will not include the Wess-Zumino term in the following. So now the meromorphic function is simplified a little bit, but basically it's the same. So then, by using these expressions, so the master formula is reduced to like this. Because now small k equals 0, so the Wess-Zumino term does not appear. So this kinetic term, only kinematic term appears. So then, in the following, we assume a finite dimensional matrix representations. So the inner bracket is simply replaced by trace. So then the boundary condition is also the same. This is exactly the same as the previous one. We will not change the boundary condition. So then we would like to try to consider a generalized ansatz for the Lux form. That is given by like this. So the pole structure is different. So now, this Lux ansatz contains k plus and k minus, in addition to the previous four holomorphic functions. So sorry, smooth functions. So this Lux form. So when k plus minus equal v plus minus, so this Lux ansatz is reduced to the previous one. So because pole structure is simplified, so if k plus equal v plus and v minus equal k minus, so y minus g is reduced, and so 1 plus g is removed. And so then we can reproduce the previous Lux ansatz. So in that sense, so inclusions of this capital K plus minus is deformations from the usual Lux pair. Okay, so then, by putting this form into the boundary conditions, so we can evaluate as in the following, as in the previous. So then, Lux form is evaluated like this. Now k plus minus are redefined like this. So then, Lux form has not been determined completely. So this Lux form still has unknown functions. So this is a big difference from the previous one. So anyway, this unknown function, this unknown function remains, but anyway, let's go to let's proceed the computations. Okay, so then the bulk EOM is trivially satisfied because the boundary condition is not changed. So then we need to consider the bulk EOM only. So then let's substitute this form into the bulk EOM. So then we will get these three conditions from the bulk EOM. So the first one should be the conservation law of curly J. So this is nothing but the true EOM for two-dimensional systems we want to obtain. And we will obtain two additional conditions. And so then, so if you know well about the auxiliary field sigma model, so these conditions are exactly the same as the constraints obtained in the auxiliary field sigma model. So in the case of auxiliary field sigma model, these last two conditions are obtained by taking variations with respect to auxiliary fields. And so in order to get these conditions, the auxiliary fields were necessary. But now, without using auxiliary field, we will get these conditions just by putting the lux into the bulk EOM. So this is a very important point. So then the analysis would be rather straightforward. But of course, there is some problem to be considered. So, okay, so anyway, so we will get these three conditions just by putting the lux form into the bulk EOM. So then we want to make some comments here. So the first one is the conservations of curly J. This is just on-shell conditions. So I mean, so these conditions should be satisfied on shell by taking variations of the true Lagrangian. But here, so please notice that, so usually, so the Lux pairs should be fixed after providing the Lagrangians. Yeah, because the EOM should be fixed after fixing the Lagrangian. But now, so these Lux pairs should be put into the original master formula Lagrangians. So the Lagrangian depends on the Lux pair. So this is something like the problem of the chicken and egg problem. So this is quite a confusing point. So usually, if we take the simple Lux ansatz, the Lux pairs can be completely determined by using the boundary conditions. So there should be no this type of problem. But so if we adapt this type of generalized ansatz, so unknown function remains. So we need to consider this type of chicken and egg problem. So this is the confusing and interesting point. So anyway, so I will answer to this problem soon. So then the second and third conditions are off-shell conditions. So these conditions should be satisfied somehow without using equations of motion. Okay, so then, so now we have arbitrary function J mu. So we would like to expand this J mu in terms of x1 and x2 I introduced yesterday. So this x1 and x2 are two independent Lorentz scalars and functionally independent. So these two quantities were introduced by Felco et al. In these papers. So by using these two Lorentz scalars and Lorentz covariance, we can expand this carry J like this. The factor 2 and 4 are just conventions. So we cannot lose generality. So anyway, so this is the most general expansions of this carry J in terms of x1 and x2. Of course, there are some choices of x1 and x2. So this is just a choice of basis. So, but here we will take this basis. And actually, so the choice of basis depends on the choice of meromorphic functions or boundary conditions. So if we change the meromorphic functions, the boundary conditions, we need to change the basis x1, x2 to x1 tilde or x2 tilde or something. But here, we will take this basis. Okay, so then, so this J mu is expanded like this. So then, this second condition is automatically satisfied. So the second condition is okay. So then, the third conditions can be rewritten into this form. So probably so you can remember the Courant-Hilbert conditions. So I explained yesterday. So this Courant-Hilbert conditions appears from this third condition. So the remaining is to check the first conditions on shell condition. So then let's consider the variations of Lagrangians. So the master formula Lagrangian is evaluated like this. So now this curly J is expanded in terms of x1 and x2 like this. And so then by putting this into the master formula, so then we will get these expressions. So now we have two expressions. Anyway, so we want to discuss variations of this first line. So in order to discuss the first condition on shell, so let's take variations of this this form, this expression. So then, so after some calculations, we obtained these expressions by taking the variations of this one. So then, so this is the resulting expressions of Lagrange variations of Lagrangian. So now we have some extra pieces. So this is a piece we wanted to derive because del mu j mu equals 0 is the correct equation of motions we wanted to derive, but still we have some pieces here. So this is a variations, but this is just a function. So, okay, so in order to simplify these expressions, we will take these answers. So we will introduce capital F like this. So F1 is derivative of F with respect to X1, and F2 is derivative of X2. So then this variation is simplified. Sorry. So by using these expressions, so this condition is rewritten into this form. So this is nothing but the Courant-Hilbert conditions I explained yesterday. So then, so the variation is also simplified like this. So the last piece is the one we wanted to derive. So this gives the equations of motions are consistent to the Lux form, the flatness of Lux form. So then, so we have this additional piece. So since the Lux form contained F1, F2, so now unknown function is characterized by this curly F. So this curly F is included in Lux form. And the Lux form is put into the master formula Lagrangians. So that's why this F appeared in the variations of the master formula Lagrangian. So the master formula Lagrangians may not be the true Lagrangians, because Lux pairs has not been determined. So anyway, but now we have good ideas to modify the multidimensional Chern-Simons actions like this. So let's see, define L hat like this by moving this piece to the right-hand side. So L hat is defined by like this. So then, by taking a derivation, variations of L hat, we will get these expressions. So L hat provides the equations of motions we wanted to derive, which is consistent to Lux form, the flatness of Lux form. So then, we need to consider the interpretations of this additional piece. So now there are two ways to see this L hat. The first one is very simple. So now L hat becomes F by using these expressions. So by using these expressions, so then L hat is simply given by F itself. So then, it is quite easy to see the relations between the Chern-Simons actions and Courant-Hilbert constructions I explained yesterday. So now true Lagrangian becomes F itself. So just a form is we may keep the original Chern-Simons action. I mean the master formula Lagrangian part. So then we can rewrite additional piece somehow. So this is the result. So the L hat may be seen as the original master formula Lagrangian plus the trace of the energy momentum tensor. So this is the second interpretation. So we can see this L hat can be seen as F itself or equivalently the original master formula Lagrangian has been corrected by adding the trace of the energy momentum tensor. And the energy momentum tensor is for the default theories, L hat, the energy momentum tensor for L hat. Actually, so that we can compute the expressions of T hat mu nu for this L hat by taking derivative for the metric. So this is the expression. So anyway, this the appearance of this the trace of the energy momentum tensor was also pointed out by Sakamoto-kun and Roberto Tateo and Masahito Yamazaki in these papers for TT bar deformation case. So anyway, so if we consider the TT bar deformations, so TT bar deformation is a relevant perturbations, and the deformation parameter is dimensionful. So in that case, we need to be careful for the Chern-Simons actions. Yeah, because Hodge-Benedict Chern-Simons action should be classically scale invariant. Yeah, because that is dimensionless. And so the classical scale invariance, but classical scale invariance should be broken when considering dimensionful parameter deformations like TT bar deformations. So that's why, so we need to add this term like this. So anyway, so the appearance of this term should be closely related to the fact the four-dimensional Chern-Simons action is classically scale invariant. So this observation was made in this paper. Okay, so then in summary, so deformed Lagrangian is given by these ones. So L hat is F itself, and this can be expressed like this. So this is these are equivalent forms. So okay, so then, so this F can be determined by solving the differential equations. This one. So this is nothing but the Courant-Hilbert constructions I explained yesterday. So then, so once F has been determined by solving these equations, so deformed Lagrangian F is determined, and so now Lux pair is given by these ones. So by determining J, so this carry, sorry, so by determining F, by solving these differential equations. And so this curly J is determined. And so then, so the Lux form is also determined. So anyway, so the everything is to solve this differential equation. So how should we determine F? So we know answer already. So anyway, some questions or so far? No. Okay, so let me explain about the Courant-Hilbert method a little bit. So as I explained yesterday, so by introducing these variables, this differential equation is simplified to this form. Okay, so then, so we know the general solutions to these differential equations. So that was provided by Courant-Hilbert. And so this curly F is written like this. So F is this one. And so this F is parameterized by L. So L is arbitrary functions satisfying these boundary conditions. So actually, so this was explained in the book by Courant-Hilbert. So this is English versions, methods of mathematical physics. So this equation, so this solution is written in the volume as a page 91 of volume 2. This is the Japanese version. So this is a page of the Courant-Hilbert solutions. Okay, so that is once L of tau is given, the home Lagrangian and its associated Lux pairs are determined. So this is a Courant-Hilbert scenario. So in the following, we shall list up some examples of L's. So actually, so the possible L's are classified. Some possible examples are classified by Luss and Townsend. So in the context of the formations of four-dimensional nonlinear electrodynamics. So just borrow their result. So I will explain some examples of L's. So the first one is undeformed case. So L tau is just tau. So then, so curly F is evaluated like this. We will get the undeformed principal chiral models, as I explained yesterday. So then, the second non-trivial one is root TT bar deformations. So so we can introduce some coefficients in front of tau. So the null tau is a dimensionless constant. So then, so curly F is evaluated like this. So this is nothing but classical actions of root TT bar deformed principal chiral models obtained by Bolsat et al. By solving the root TT bar flow equation directly. So in this case, the modification term is zero. So because this is a marginal deformation, so the trace of the energy momentum, trace of energy momentum tensor becomes zero. Okay, so in this case, we don't have to include the correction term to the original master formula Lagrangian. So then let's see the TT bar deformation case. So by considering this L, we can evaluate curly F like this. So lambda is now dimension full parameter. So then classical invariance, classical scale invariance should be broken. So then, so the trace of energy momentum tensor is not zero. So that is given by this one, determinant of energy momentum tensor. So this expression was obtained in Sakamoto-kun et al. Papers, this ones. Okay, so then we may consider as possible generalizations and the mixtures of TT bar deformations and root TT bar deformations. So this is given by this one. So then, so we can get this a bit complicated classical Lagrangians. So this was obtained by Felco et al. In these papers by solving the flow equations, general flow equations. So in this case, energy momentum tensor, the trace of energy momentum tensor is not zero. So then, this is more non-trivial one. So this is log type deformations. So this log type of deformations was found by solving the Courant-Hilbert problem originally by Luss and Townsend in these papers as the deformations of Maxwell theory. So anyway, so by using this solution, this L, we can get the deformed actions like this. This action was obtained by Babae et al. In these papers. So they borrowed these expressions and they get the deformed Lagrangians based on this. So this lambda is also dimension full parameters, and so also in this case, the trace of the energy momentum tensor is not zero. Okay, so then let me summarize my talk. So here, so I have explained integral deformations of principal chiral models based on the Courant-Hilbert method. And this Courant-Hilbert method includes TT bar deformations and root TT bar deformations as famous examples. So anyway, so this scenario was proposed by Babae et al. In this paper. So then we have discussed how to consider the Courant-Hilbert method in the framework for the Chern-Simons theories. So in order to incorporate Courant-Hilbert constructions, we have generalized Lux ansatz by changing the pole structures and including arbitrary functions. So then, as a result, the original for the Chern-Simons actions should be corrected by adding the trace of the energy momentum tensor. So this is our claim, and so this trace of the energy momentum tensor is consistent to the result by Sakamoto-kun et al. Okay, so then let me list up some future directions. So first of all, so we need to check the universalities of the collection terms. So here we have derived the collection term, the trace of the energy momentum tensors by considering the principal chiral model only. So, but by changing the seed theories, by changing the metabolic functions, we can consider a lot of examples systematically. So of course, we need to take appropriate basis x1 and x2. So it is not so non-trivial, but basically straightforward to check the universalities of the collection term. So I want to check the universalities of the collection term by considering different seed theories, by changing metabolic function, or by changing the boundary conditions. For examples, by changing the boundary conditions from the trivial ones to the non-trivial ones, like Yang-Baxter deformations. Okay, so then second one is the physical conditions in the Courant-Hilbert conditions. So I have just mentioned about physical conditions of the energy momentum tensors in the panel discussions yesterday. So please remember the form of the energy momentum tensor is given by this ones. So this L hat is nothing but F. So for general F, so this energy momentum tensor is not physical. So we need to impose some physical conditions for this energy momentum tensors, positive energy conditions or NF conditions or some conditions, or causality is also important to consider this type of deformations. So these physical conditions are well discussed in the context of four-dimensional nonlinear electrodynamics. So these conditions should also be considered in the context of two-dimensional integral models, I think. Yeah, of course, integral models are integral models. So without imposing physical conditions, we can get integral systems. But integrability is, of course, important for us. But physical conditions should also be important, I think. Causalities or something like that. So, for example, in addition, so in the case of the four-dimensional nonlinear electrodynamics, the weak field limit is important as well. That corresponds to undeformed limit in the context of two-dimensional integral sigma models. So if we don't impose the weak field conditions, so we cannot recover the original theory. So that non-invertible examples are also possible. So for example, so here, this is a root TT bar. So this is a TT bar deformations, but here, so I took the minus signatures. But so for minus signatures, we can well define the undeformed limit. But if we take the plus signatures, the undeformed limit is not well defined. So in this sense, so the deformation is not invertible, but still integrable. So integrability is preserved, but undeformed limit is not ensured. So we should be careful how to interpret the deformations based on the Courant-Hilbert constructions. So probably we need to impose some physical conditions, and so the meaning of these conditions in the context of two-dimensional integral models. And so we are interested in quantum integrability as well in the Courant-Hilbert construction. Of course, the Courant-Hilbert constructions includes TT bar deformations and root TT bar deformations. Of course, the TT bar deformation is well defined even at quantum level, but we are not sure for at root TT bar deformations. So based on these observations, some examples in Courant-Hilbert constructions are quantum integrables, but the others are not. So I want to classify quantum integrable ones by imposing some physical conditions or something. And also we got the correction term, the energy moment to the trace of the energy momentum tensors that may be related to six-dimensional holomorphic Chern-Simons theories. And so this may be related to the 4D with Zumino-Witten models. So this is unified pictures. And so as Hamanaka-san explained, so we can see like this. So here we consider the Courant-Hilbert constructions, and we got the appearance of the correction term. So probably I think that we can consider the Courant-Hilbert constructions in other theories, and the correction terms should be related to these theories. So especially the trace of the energy momentum tensors should be closely related to this classical scaling invariance of these four-dimensional theories. But this six-dimensional theory is not classically scaling invariant. So in this sense, it should be better to consider six-dimensional holomorphic Chern-Simons theories to study the origin of the correction term. Okay, so anyway, so as further possibilities, we may consider applications of Courant-Hilbert constructions in the context of ADS3 CFT2. So the ADS3 or S3s are described by principal chiral models. So then we can consider deformations of ADS3 and S3s based on Courant-Hilbert method. And so for example, the deformations of AD3 should correspond to the deformations of conformal field theories. So probably by using this Courant-Hilbert method, it may be possible to new kinds of deformations of conformal field theories. Okay, so yeah, this is last slide, and so I will stop here.
Okay, thank you very much for very clear talk. Okay, is there any questions or comment from the whole pass? We have enough time.
I'm sorry. Can you explain more more in detail in the previous slide, maybe?
Oh, this one?
The universalities of the correction term. What do you mean by that?
Okay, so we got just a simple expression of the trace of the energy momentum tensor. But so if we change the Shield series from three-dimensional principal color model to another series, so the correction term may be functions of the trace of energy momentum tensor, for example. So this is just a simple expression, right? So fx equal x, and so this term may become more complicated form as a possibility. So that's why I want to check the universality of these expressions.
Okay, is there any other questions or comment? Okay. Okay, so from online, do you have any questions or comments? You are free to unmute your mic or write the chat message. No question? Very clear? Okay, if not, let's thank the speaker again. Thank you very much.